Hello, everyone. I'm Ricardo, and I'm a PhD student at the AVS lab at the University of Colorado Boulder. And today I'm going to be talking to you about a Basilisk-based benchmark analysis of different constrained attitude dynamics planners. First of all, what do we mean with constrained attitude dynamics? We mean maneuvering a spacecraft that has hard positional constraints, such as keep-out constraints, which can be sensitive payload that we do not want to point at a bright celestial object, or a keep-in constraint when we have an instrument such as a sun sensor that we want to keep pointing at a certain celestial object while we perform the maneuver. Many solutions exist to this problem, but they're usually very different from one another. Some rely on Lyapunov theory, others rely on some kind of path planning algorithms. The problem is therefore how to compare these very different algorithms. Also, based on the fact that many of these solutions are problem-specific or come within problem-specific scenarios. So whenever a new implementation for a new mission, for example, needs to be simulated, we need a tool that allows to compare these different algorithms and their performances against the standardized scenario. The purpose of this work is to assess the feasibility of using Basilisk Astrodynamics simulation framework to provide such a scenario. So first of all, what is Basilisk? Basilisk is an open source software that can model very complex spacecraft behavior. This software is being developed by the AVS lab and LASP at CU Boulder. And the main features of Basilisk consist in its C and C++ core, which makes computation very fast, combined with a Python interface that makes it very easy to modify and reconfigure scripts to run different simulations. Another key feature of Basilisk is its modular structure, which allows for minimal coupling between different segments of code, which makes it easier to remove or replace a module within the simulation without having to change the entire structure of the code. Basilisk also comes with a rendering tool, which is called Wizard, which allows to visualize the simulation that has just been run. The scheme highlights all the modules that are used in the simulations that I'm going to be showing to you in a few seconds. Each of these boxes is a different module, and each module simulates some spacecraft behavior. We're going to be focusing on the waypoint reference module and the path scorer module that were developed specifically for this work. And I just want to highlight the fact that a custom module can be written by any user and in substitution of the waypoint reference module. So the waypoint reference module can read a slew maneuver that was likely computed outside of Basilisk using some kind of constrained attitude path planning algorithm. And this maneuver can be read from a data file containing time-tagged attitude waypoints. Such attitude waypoints must be provided as modified Rodriguez parameter sets or quaternion sets, and they should come with the desired angular rates and accelerations at each of the waypoints. Currently, Basilisk does not feature a guidance algorithm that can perform constrained attitude maneuvering, but one such algorithm is currently being developed and is going to be released in the next few weeks or months. And again, the user can use the waypoint reference module to read a maneuver from an external source, or can implement their own custom module that implements whatever guidance algorithm that they desire and incorporate it into Basilisk. The path scorer module computes a number of performance metrics to assess the performances of the different planning algorithms. These performance metrics are the total keep-out violation time, total keep-in violation time, the attitude error integral between the simulated attitude and the reference attitude, the commanded torque integral, and the total energy required. And the 4 different planners that are used in this work are described here. Planner 0 is a constraint-naive planner that just relies on the initial and the target attitude, but completely ignores the constraints. Planner 1 relies on a breadcrumbs approach, where the reference is provided in terms of a sequence of constraint-compliant attitude waypoints with zeroed angular rates and accelerations. So the effect that this has on the simulation is that the spacecraft is trying to target different attitudes, but it's also following a moving target. Planar 2 uses the same attitude waypoints as Planar 1, but these attitude waypoints are interpolated in MRP space. This allows to also provide angular rates and accelerations along this interpolated trajectory, which performs a rest-to-rest maneuver. Planar 3 relies on the same philosophy as Planar 2. However, in this case, the interpolated trajectory is based on a set of waypoints that are searched using an A-star algorithm that tries to minimize the integral of the control torque required to track the interpolated trajectory. The spacecraft and its constraints are modeled after the Bevo-2 satellite, which has a sensitive camera aligned with the X body axis and 2 sun sensors aligned with the Y and Z body axis, one of which must be able to see the sun at all times. 3 reaction wheels provide actuation, and the control torque is found in the expression on this slide, of which I just want to highlight the fact that 2 control gains must be picked as a design choice, and these control gains can have a pretty strong impact on the performance of the simulations, as we're going to see in a couple minutes. Here we're showing the performance metrics for the 4 planners, where we see that as far as the keep out violation time, none of the planners do violate the keep out constraint. The same cannot be said about the keep-in constraint, where we can see that only Planar 3 is able to not violate such constraint. The control torque integral is more interesting in the sense that we see that Planar 3 outperforms Planar 2, which is exactly how Planar 3 was designed, which is to optimize for the required control torque integral. However, the surprise here was to see that Planar 1 outperforms Planar 3. And the reason why this happened is that the breadcrumbs approach used by Planar 1 consists in trying to have the spacecraft follow a series of attitude reference points, but the spacecraft is not able to do that. So what happens is that the simulation is smoothing the reference that is being fed to the attitude tracking module. And this is why ultimately the track trajectory is smoother and cheaper in terms of control torque required. And the same thing applies to the total energy consumption. More interestingly, in the attitude error integral, we see that Planar 2 and 3 are 3 orders of magnitude better than Planar 0 and 1. And this means that the reference that is fed using Planar 2 and 3 is much easier to track than the other 2. Also, all these simulations were run using these control gains that I'm highlighting here. So it's interesting to see how these simulations changing the control gains. So this is what is shown right here, where the control gains can span 2 orders of magnitude. And we see that the solid lines are the average curves obtained with all these different gains, whereas the opaque areas are upper and lower confidence bounds obtained with best and worst case scenarios, respectively. As far as keep out constraint, we see that none of the planners violate such constraint. Keep in constraint can be violated or not by Planar 1, depending on the gain choice. But more interestingly, if we look at control torque integral and total energy consumption, we see that Planar 1 is very susceptible to gain choice. The performance can vary significantly based on the gain choice, whereas Planar 2 and 3 don't seem to be affected by the gain selection. This is even clearer looking at the attitude error integral, where we see that the worst case scenario for Planar 2 and 3 is still 1 order of magnitude better than the best case scenario for Planar 1. This means that when a precise and smooth reference trajectory is fed to the attitude tracking error module as the one used by Planar 2 and 3, the simulation becomes robust to gain selection. In conclusion, Basilisk can be used to provide reliable standardized scenario for different path planning algorithms and enables the user to implement slew maneuver either computed externally or to write their own guidance module. Different performance metrics can be analyzed in Basilisk, and simulations are successful at detecting constraint violations and offer insight on how easily the spacecraft can track a reference trajectory. Simulations highlight the necessity for a time-dependent, precise reference trajectory instead of a breadcrumbs approach to obtain precise tracking. When such a trajectory is provided, the problem becomes robust to gate selection. If you have any questions, feel free to reach out to me. This is how you can do so. And in the meantime, I would like to thank you for your attention and wish you a nice day.